In this devlog, we'll be exploring the world of deep learning by implementing a neural network in C++. Now, when I try to look for other tutorials on the internet, most of them use a high-level language like Python and even used a third-party library like TensorFlow to implement the neural network, which is all good. It actually gets the job done really quickly, but I'm after the learning process wherein if you want to learn a particular algorithm, then you take that the way the algorithm works and break it down into different components and try to implement each component one by one from scratch. So it's not really about reinventing the wheel, but rather it's about trying to study how a particular algorithm works through code. And the reason why I used C++ as opposed to a high-level language like Python is because eventually I'd like to explore GPGPU, which is general purpose GPU computing, wherein it will take advantage of the computer's graphical processing unit to solve for a complex problem. For example, in the case of most machine learning algorithms like neural networks, there's this training phase wherein the algorithm will try to learn something from a particular data set. And if your data set is too large, then it might take days, weeks, or even months to finish that training process. By taking advantage of the GPU, you can actually cut the training phase shorter by taking advantage of parallel computing. So to start things off, the first thing I'll implement is the most basic building block of a neural network, which is the neural network's neuron. Now, all the neuron will do is that it will actually hold a value. Okay, before I go into that, I have here the project called OpenENN, wherein I believe there's actually another project called OpenENN. But just for this particular exercise, I'll just name this project OpenENN. But it's different from that other OpenENN project. Okay, so the structure here is actually from the first C++ video I did, wherein you can organize your C++ project this way by making use of CMake to define how you would compile a project. So here I have the executable OpenENN, and then after that I have the source files that would compile to the binary OpenENN. So what I'd like to do is that I'd like to have something like this. I'd like to have a class called Neuron, which will hold a value every time it's constructed. So if I do something like new neuron, I'll have a value there, let's say 0.9, and that will define the neuron class, or the instance of a neuron. Now, the way neurons work in neural networks is that it can hold values that are either the input values or some processed value wherein it transforms some information into a single summarized version according to some weighted values. Right? So for example, if I had 3 neurons, this would probably mean something like define a characteristic of something we'd like to learn. So for example, this one might refer to a dog, wherein the observable data for a dog is 0.9, 0.5, and 0.1. So these neurons will actually represent that dog, and then we'd like to learn this particular pattern and say that, okay, given these values, this one is actually a dog. Right? So this is otherwise called our input neurons, wherein these neurons would hold values relating to the input data of our dataset. Now, for a typical neural network, it would also have an output that would also represent a particular neuron. Right? So let's say we have an output neuron whose initial value is probably 0. Right? We don't know, this particular neuron will define the classification of what we're trying to learn. So if in this case this were a dog, 0 0.9, 0 0.5, and 0 0.1, then the output neuron would be a compressed version, not really compressed, but a processed version of this particular pattern, and say something like, okay, I'm 90% confident that the feature vector, the pattern 0 0.9, 0 0.5, and 0 0.1 is a dog, right? So meaning the output neuron is actually 0 0.9, because we want to be 90% confident that this thing is actually a dog. Right, so we'll get into the training part later on, but the first thing we have to do is to implement the neuron so that we can call it this way. Right? Okay, so just remove that there, and we'll just have n right there. Okay. So let's first test this. So if you try to compile this, of course it will produce an error because we haven't defined yet what a neuron is. So the way I'll define a neuron is that I'll first create a header file for the neuron. I'd like to keep things as organized as possible, so I'll start with the header file. I'll have a guard right here, if and define neuron HPP, then define neuron HPP, okay, and if. Right, so I'll have a bunch of header files here for standard stuff, and I'll have the definition of my class neuron right here. Right, so for my class neuron, I'll have a public and a private section. In the private section, it will only hold the current value of that neuron. Okay, so in this case, for the pattern for a dog, it might be something like 0 0.9, 0 0.5, and 0 0.1. But the idea is each neuron will only have exactly one value representing that neuron. Now, another thing I'd like to do is to also have two more values. An activated value, right, which will hold that neuron's activation value, which is the squished version of this value, right? When I say that it's a squished version of this value, it means that it will fit this value to a certain range. So for example, if we had the value of something like 1.5, I'd like to activate that value. I'd like to squish it to a range from something like 0 to 1, right? Because if you, it works, I guess it works the same way as normalization, but the concept is that given a neuron's raw value, you'd like to have an activation function that will force that value to fit within a certain range, making it easier to compute. Right? But if you go through the mathematics of it more formally, you'd want to do that so that the value will fit into a nonlinear function, so that the network will solve nonlinear problems. If you use the raw value, you're actually assuming that the network will be solving linear problems. Right. I'm not sure if I actually said that correctly, but I think it goes something like that. Now, aside from having the activated value, you'd also like to have the derived value, just call it derived val, for that neuron. The derived val is actually the value, the approximated derivative of the activated value. Right? If you look at the other implementations of neural networks, you'll see that it will activate a particular neuron's value, and then when it tries to train the network, it will get the derivative of that particular value. So my current implementation for the neuron, it might not be the most efficient way, but basically I have the raw value, the activated value using some activating function, and the derived value, wherein we'd like to take the derivative of the activated value. Now, speaking of derivatives, the way I'd like to activate it is by using the fast sigmoid function. Okay, so our activation value, or our activation function, which I'll define as void activate, will be based on the fast sigmoid function. Okay, I'm not sure if I said it right. Right, so given a particular neuron's value, I'd like to activate it using some nonlinear function. In this case, I'd like to use the fast sigmoid function because that's actually the easiest, I think that's the easiest activating function to implement. We're in to compute for the fast sigmoid, that's actually equal to, let's see now, I think x over 1 plus the absolute value of x, right? So the fast sigmoid is x over 1 plus the absolute value of x. So to get the derivative, no, the reason why I chose the fast sigmoid function is that it's actually easy to get the derivative for this fast sigmoid function. The derivative for fast sigmoid function is equal to just f of x times 1 minus f of x. Right? For some tutorials, they have this whole proof on why this is the case, but in this case, I'll just be using these two formulas for it. Okay, so I'll call this derive. So it will derive the activated value, and then it will store that derived value in the derived val variables. Okay. What else? So I'd also probably have some getter functions, right? So I can just print out whatever the value, the raw value is. So I'll have get val, and then I'll implement it here directly. So return this val. Right? I'll also have get activated val, which will just return the value for activated val. And of course, I'll also have get derived val. Double get derived val. Right, so one more thing I need will be the constructor. So neuron double val. So I'll require all my neurons to always have a value passed to it every time it's constructed. Okay, so that it will actually fall under this this syntax, neuron n equals new neuron, and then you pass a value to it, let's say 0.9. Okay, so once we have our blueprint for our class neuron, the next thing to do is to implement these functions, the activate and the derive, as well as our constructor. Okay, so I'll start with the constructor. Oops. Okay, so I'll start with the constructor by first creating the source file neuron.cpp, right, which is the implementation of my neuron header file, or the neuron class. Okay, so I'll include first the header file. If you notice, the header file is inside this directory, which is one level from the source file .cpp. So to include the header file, I'll go one level up, go to the directory include, and then neuron.hpp. So I have everything there. Okay, so I'll first implement the constructor. So the constructor is just neuron neuron double val, and all it will do is it will first set the current value of this neuron to whatever value you pass to it, and then it will activate this value, right, and it will get the derived version of this value. Okay, so sequentially what we do is, given a value that we pass to a new instance of the neuron, store it in the val variable, activate that value, and then derive that value. Okay. If you notice, the return type of these functions are void, so it's what I'm trying to get at here is that it will set the value, right, for activated val and derived val for these by using these functions respectively. Okay, so to implement activate, let me just copy our notes here for fast sigmoid. Okay, so we have neuron activate. It's in the fast sigmoid. We're in the activated value. Activated val. Activated val is equal to the current value, the raw value, this val, over 1 plus the absolute value of the value itself. So this val. Okay, I think we can call something like math.abs. If I'm not mistaken, right? Math.abs to get the absolute value of whatever that value is. I'm not sure about this function, so maybe we'll find out if this is correct later on. Okay, now for the derivative, we have here void derive. So I'll copy this note again. Okay. And then we have a function signature right there. Derive. Okay, I forgot to include the return data type. So this one is void. This one is void as well. Right. So the derivative of the fast sigmoid function, the approximated derivative, is f of x times 1 minus f of x. So this derived val, just check if that's the correct variable. So yeah, this derived val is equal to this activated val, okay, multiplied by 1 minus this activated val. Okay, so it will set the value for the current activated val by using this function. Okay, I think this one is correct. Okay, so those are just the 3 things that we need to implement for now: the constructor, the fast sigmoid function, and the derivative for the fast sigmoid function. Okay. I think we need to include math here. Math.h or something. Can't remember. I think it was just abs. Absolutely. Anyway, we'll find out once we compile this program. Okay, so once we create a new instance of the neuron, then we can examine the values. So we just print out some stuff. Let's say val is n get val. Right. And then we have one for activated val, get activated val. And then we have one for derived val, derived val, right? Right, so let's see if this works. One more thing, I have to make sure that whenever I compile this program, I actually include the neuron.cpp file. Okay, let's try to compile it. Okay, cmake.make. Okay, so neuron was not declared in the scope. Neuron was not declared in the scope. Oh, okay. So, yeah, I forgot to include the header definition as well in the main.cpp file. So neuron.hpp. Alright, so main will now know what the neuron class actually is by including the header file right there. Okay, so we don't make. Oh, okay, so we have a bunch of errors here. Neuron. Okay, I see one here, line 18 of neuron.cpp. I misspelled it as neuron with U before E. It should be E before U. Okay, so let's see. Let's go back to that. Let's search for neuron. Okay, so let's replace all neuron with the correct spelling of neuron. Oops. Okay, let's try to compile it again. Oh, okay, so it worked. Let's try to run the neural network. Okay, so So I guess it worked. You have the neuron class whose initial value is 0.9. Activated val is that thing right there using the fast sigmoid, and the derived value is 0.25. 249307. Okay, so for this session, all we did is to implement a neuron class that has the capability of accepting a value and activating that value using the fast sigmoid function so that it forces the value to be from a range of 0 to 1. Okay, so we can actually play around that domain of numbers 0 to 1. And then we can take the derivative of that number by using this equation to derive the fast sigmoid function, or to get the derivative of the fast sigmoid function. Actually, I'll call this derivative. Derive. I think derive is much better. All right, derive. Okay, so what else? Oh, let's do more tests. So let's say I pass a value of 1.5. It should fit this number into a range from 0 to 1. Okay, so I compile this again. Right, so 1.5, the activated val for 1.5 is 0.6. And then the derived val is 0.24. Right? Right, so that's it for this this introductory coding session, or introductory session for neural networks. All we did right here is to create a simple neuron class that implements some of the most basic functionalities of what a neuron does, which is to activate itself using some nonlinear function and to get the derivative of that nonlinear function. It's not an exact derivative. I think this is just an approximate of that value. Okay, so for the next sessions, we'll be extending our neural network and probably to start programming the weights and matrices of the neural network. So that's it for this live coding session.